we'll connect them with statistical physics. Alex, it's a pleasure to have you here.
Great. Well, thanks so much for having me. Thank you all for being here. So yeah, this talk will be kind of about connecting two different heuristics for predicting computational hardness and statistical problems. Statistical physics on one hand and low-degree polynomials on the other hand. I think many of you are somewhat familiar with the statistical physics side, and I'll maybe assume a bit of knowledge with that stuff, and hopefully that will be okay. I'll suspect many of you are a bit less familiar with the low-degree polynomial side, and I'll try to explain kind of what this means. So the style of questions I want to talk about is what we might call high-dimensional statistics. So I'll give just a couple of very canonical examples of this. So high-dimensional statistics, generally means there's maybe some kind of a planted signal that we want to recover, but it's hidden within some kind of large random noise. Or the random noise might be a big random matrix or a big random graph. So here's one basic example would be the spiked Wigner model, which is basically a rank 1 matrix plus noise. And when I talk about these things, I'll actually make two different distributions that the data might be drawn from. There's the planted distribution, which has the hidden signal we want to recover. And then there's also the null distribution, which is just pure noise with no planted signal. So in this case, for spiked Wigner, planted means that I observe a matrix, n by n matrix Y, which would be, the rank 1 part where U is the vector U is a hidden signal. Lambda is like a number, which is a signal to noise ratio, plus this kind of random Gaussian Wigner matrix. Whereas in the null case, you just get the Wigner matrix with no signal. Another kind of very canonical problem in random graphs is called the planted clique problem. So we have Gn1/2, meaning the random graph with n vertices, and every pair of vertices gets connected with probability half independently. But in the planted case, we also hide this hidden clique. So pick k vertices at random and then connect them all to each other if they weren't already connected. And so, these style of problems, one thing, this is kind of blocking the view, but one thing that's kind of, a well-known phenomenon that we are kind of intrigued by in all these problems is the idea of a statistical computational gap. So for example, in this planted clique problem, this was sort of one of the earlier examples where, k is the clique size, which is kind of the signal strength. So the problem should get easier as k increases. And the problem goes through these three different phases. So if you plant a clique that's really small, it's simply impossible to find it or to even detect whether it was there or not, because this is like the largest naturally occurring clique in the random graph. And so if you plant something smaller than that, it just sort of gets lost. On the other hand, if you plant a very big clique, bigger than square root of n, we know fast algorithms to find it. That's sort of what we mean by easy. So easy means there's like a polynomial time algorithm that provably finds this thing with high probability. Okay, but then in the middle, we have this hard regime where in principle, you can find the clique by a brute force search, but we don't know any fast algorithm to do it. And we are starting to suspect that maybe this is fundamental, that, we've tried for 30 years or whatever, and we think maybe there just isn't a fast algorithm. But, how do we know for sure? Do we need to just try harder to find a better algorithm in this hard regime? Or can we actually prove in some sense that it's fundamentally hard? If we can prove it's hard, that kind of lets us stop wasting our time looking forever for a better algorithm. So that would be nice. And we have a bunch of different communities have come together with different ideas of what makes these problems easy, what makes them hard. So here are some examples here. Coming sort of from the statistical physics viewpoint, we have approximate message passing and the associated replica symmetric potential. But then, various other heuristics as well. Overlap gap property is some kind of structural property of the solution space that can be used to rule out certain local search algorithms. Sum of squares hierarchy is some kind of complicated hierarchy of very, very large convex programming problems. Statistical query model is some restricted form of algorithms that only get to ask certain questions about the data rather than seeing all the individual samples. And then low degree polynomials is one that I'll talk about a lot today. And so with all these, by now we have many results saying that like, oh, planted clique problem is hard for these algorithms, it's hard for this and hard for this, and same for all these other problems. And so when a new problem comes along, what do we need to do? Do we want to like separately analyze all of these things? I mean, it would be kind of nice if we could actually unify this theory, maybe prove that all of these things actually make the same prediction, so that when a new problem comes along, we only need to prove one type of hardness rather than, writing 5 different papers. And so, this sort of goal will be the main focus of this talk. But the goal is not, the reality is not so simple. I think there's 2 kind of significant issues with this, which is first, sometimes they just aren't equivalent. And second of all, often they're not even answering the same question. So I'm going to expand on both of those points in the next few slides. And also please stop me if you have questions or anything. Yeah, good so far. So using planted clique as a running example, there's really a lot of different objectives that we might have in mind when we talk about these kinds of problems. So one simple goal would be detection, also called testing or hypothesis testing. This would be, can you even tell if the planted signal is there or not? Right, so decide, I'm going to give you a random graph. Either it has the planted clique or not. You have to just distinguish the 2 cases. Whereas the recovery or estimation problem would be actually finding the planted clique, right? You actually have to figure out which vertices have the clique. And there's a few other variations that are sort of popular as well. The next one I would call optimization. And the key thing about this is that it's non-planted. So we're going to be given a graph that comes from the null distribution. There's no hidden structure there at all. It's just totally a random graph. But your goal is just to find the largest clique that you can find. Okay, so this is like optimizing a purely random objective function. And recovery and optimization look kind of similar, but there's a key difference, which is that in recovery, there's one planted clique and you were trying to find that one. In optimization, there's like many reasonably large cliques that occur sort of by accident, and you want to just find any one of them. Right, and so, you can imagine that in the planted clique, the recovery question would be interesting for somewhat larger values of the clique, right? The planted clique should be bigger than the biggest naturally occurring clique. Whereas here, we're just trying to find a naturally occurring clique. And so we hope to find something much smaller than in this case. Okay, and the last one is maybe a little bit more esoteric or something. This particularly comes up a lot for when people are thinking about like sum of squares, because sum of squares is some kind of proof system that tries to prove that your graph has no k-clique in it. The refutation question would be to, given a graph with no planted structure, you have to algorithmically generate a proof that there's no k-clique. But I won't worry so much. This one won't be so important for this talk. And we might wonder, how are these things all related? Well, here's kind of a picture of the typical kind of formal relations between these two, between all these things. Like a lot of them are not really formally related, but it does tend to be the case that detection is easier than both recovery and refutation. So like if you could recover the clique, you can also distinguish whether it's there or not, for instance. But I think the main point I want to make here is that all of these tasks can have different thresholds in general. So it's not like all these things are the same. These really are fundamentally different questions. And it kind of matters which one we think about. And so, when I presented the different heuristics for hardness on the last slide, at first, maybe it kind of looks like they're all sort of answering the same question. But in reality, they're kind of not, because some of them apply to detection, other to recovery, and so on. And some of them can do multiple. But the situation's somewhat complicated. And yeah, one reason I'm especially excited about low degree polynomials is that they can do all of these things, which puts them in sort of a central location for tying together the other methods. Yeah, any questions about this? Maybe I won't go through the specific details of what all these check marks mean, unless someone wants to ask something. Yeah, good. So that was kind of one of the 2 points about how these different heuristics are not necessarily even answering the same questions. The other point I wanted to make is that sometimes they just aren't making the same predictions. And there's this problem called tensor PCA, which is a good sort of counterexample for a lot of these methods. That's good for kind of illustrating how they can all be different. So tensor PCA, the formal definition of the problem is not even so important. It's kind of like the spiked Wigner model, but instead of an n by n matrix, it's like an n by n by n tensor, right? Just a grid of numbers that also has kind of a rank 1 signal part plus Gaussian noise. And what's somehow surprising about this problem is that we've realized that, AMP, and, for those of you familiar with AMP, you probably know that it's, tends to be very reliable about predicting exactly when things are hard and easy. But for this particular problem, it kind of gets the wrong threshold. It's strictly worse than the best known fast algorithms, which is maybe kind of concerning. And similarly, the overlap gap property and other local search methods, predict that same wrong threshold. And then also the statistical query model predicts like a different wrong threshold. But low degree polynomials and sum of squares kind of get the correct threshold, meaning that it coincides with the best algorithms that we know, while these other types of methods are kind of suboptimal. So that's sort of a surprising and concerning thing. And there's been some various works on sort of redeeming these approaches, right? Can we like fix AMP to make it now work on par with the best known algorithms? Can we fix, local algorithms like gradient descent? Can we fix Markov chains? And yeah, it turns out, yes, a lot of these things can be done. Although the fix tends to be somewhat problem specific. I think we don't have a general way to, to always know how to fix all these things for any given problem. Yeah, please.
So when you say suboptimal threshold, you mean it overestimates the signal you need?
Yeah, that's exactly right. Like there's some signal to noise ratio. And the AMP doesn't start working until the signal is quite a lot bigger than what low degree polynomials would need. And this is bigger by like some factor of n. It's not even a question of constant factors. It's like the scaling is sort of wrong. Does that make sense? Yeah, thanks. Other questions? So, okay, I've tried to emphasize here that there are sort of many, many caveats and all these things are not exactly the same, but still there are we have made a bunch of progress on finding connections between these different heuristics for hardness. And I think the heuristics, I want to kind of separate them into these 2 groups, although maybe it's kind of a oversimplification to say that there's kind of the ones that maybe inspired by statistical physics that tend to be sort of geometric in nature, versus the ones that are kind of inspired by computer science and tend to be a little bit more algebraic in nature, using polynomials and stuff, for example. And we have and this includes both like algorithms, sort of classes of algorithms that we like to analyze, and also kind of methods for hardness. So, free energy barriers and structural properties that that we think maybe suggest hardness. And so there's various kind of formal connections that have been established here with there are lots of caveats that I'll hide, right? Like each of these results has lots of assumptions about for which problems does it work and all this kind of stuff. But, to give you sort of an overview, for example, we know that overlap gap property can be used to rule out AMP algorithms in non-planted settings. We know that sum of squares algorithms can be turned into spectral methods. That is, methods that use the leading eigenvectors or eigenvalues of a matrix. And we know that spectral methods can be turned into low-degree polynomials kind of by doing power iteration. But there's enough caveats here that you cannot chain these two implications together. We know that belief propagation can be sort of linearized in various ways to help find the right spectral methods. We know that sum of squares can simulate AMP algorithms and furthermore do it in sort of a robust way. The overlap gap property can be used to rule out low-degree polynomials. That's in non-planted settings. This will be something I talk about later, but there's some connection between low-degree polynomials and some, geometric version of free energy barriers. Also, some kind of known rigorous connection between low-degree polynomials and statistical query model. Some kind of equivalence between AMP and low-degree polynomials for a given problem. And then finally, very recently, a connection between this free energy barrier and statistical queries. So, okay, that's, maybe some kind of overview of the known results. Yeah, I don't know, any questions about any of this? Okay, so that was sort of a, high level overview of this area, but what I want to get into for the rest of the talk is, two more specific stories about trying to connect, sort of physics with low-degree polynomials. The first one is about what we call the annealed Franz-Parisi potential, and that's about connecting the low-degree detection question with some kind of a physics-style object. And then the second one is about relating the performance of AMP with low-degree polynomials, and that's in the setting of estimation or recovery. Good, let me see how I'm doing on time. Okay, so part one is about this sort of Franz-Parisi potential, which I'll explain a bit later what this means. Okay, so for this part of the talk, we'll be focusing on this testing question of, can you distinguish two cases? So if you take the planted clique example, imagine, can you tell the difference between the graph that has the planted clique versus the one that doesn't? And if we go back to classical statistics, there's a lot of well-established theory around this. So the optimal thing to do, if you don't care about computational power, is called the likelihood ratio. It's dp dq. Basically, what that means is for the observed graph y, you calculate what's the probability I would have seen this if the real distribution is p, what's the probability that I would have seen this if the real distribution is q, and you just divide those two things. Right? Hopefully that's like sort of intuitive why that would be, thresholding this thing would be kind of the best test you could do. And the situation that we will care about is one where you have some kind of planted signal, which I'll denote as U. So you can think in the clique case, U would be like maybe the indicator vector for which vertices are the clique vertices. So it would just be a vector of zeros and ones. And in that sort of case, the likelihood ratio, because this planted distribution is a mixture over all the possible clique locations, the likelihood ratio is also kind of an average over the clique position of all the individual likelihood ratios. So this expectation over U here means that U is being drawn from just whatever is the prior distribution of U in the planted distribution. So for example, here, imagine that the expectation over U means that you just pick a uniformly random choice of k vertices for the clique. And then this L sub U is kind of this restricted likelihood ratio, right? So P sub U is the planted clique distribution for that one specific choice of where the clique is. And LU is the sort of associated likelihood ratio for that. And for all these problems, it's really important that that U is drawn randomly from many different possibilities, right? Like the problem would be too easy if I told you either there's no clique or there's a clique in this one specific location, right? Because you just kind of have to check that one location. So to make the problem sort of difficult, it's really important that we're actually hiding the clique in a random spot. Yeah.
The clique problem, for instance, distribution of one is given the location of the clique, then you generate the rest of the graph.
Yeah, perfect. You can think of it kind of this two-stage process where first you choose the location of the hidden clique, and then you draw each edge kind of independently, where the clique edges have probability 1 and all the other edges have probability 1/2.
So you could not optimize the localization of the position of the clique once the graph is around generated.
Yeah, that's right. Here we're imagining that the clique location is chosen independently from the rest of the edges. Yeah. Great. Other questions? Okay, so if we take sort of the physics view, this, I believe, is what many of you might think of as a partition function, or, right, partition function in the sense that we're kind of, this expectation over U is kind of like a sum over all the possible states. Think of a choice of U as like sort of a configuration. Okay, and so going back to classical statistics, there is this tool that is called the chi-squared divergence that's very useful for answering, when is it possible to tell these two things apart and when is it not? So just for conventional reasons, it's really the chi-squared divergence plus 1, which is closely related to this stuff. But this chi-squared divergence plus 1, all it is the expected value of the likelihood ratio when Y is drawn from the planted distribution. But that's actually the same as saying the expected value of L squared when the graph comes from the null distribution. And that's just because dp dq kind of changes measure from an expectation over, if you have an expectation over P, you can change that to an expectation over Q, but you have to throw in a factor of dp dq. And then finally, if we use the form of the likelihood ratio here, where it's sort of an average over all the different choices for U, we can kind of expand this out like this, where now U and V are two independent replicas, two independent choices for the clique location, which still here are just chosen uniformly at random. Good so far? And in physics, I believe this would be called the annealed free energy, or maybe the logarithmic of this would be the annealed free energy, I suppose. And in statistics, it's kind of well known that if this thing remains bounded as n goes to infinity, so we're always kind of imagining, think of the limit of large graphs. So the graph size n goes to infinity. We want to succeed with high probability. That is probability tending to 1 as the graph size goes to infinity. So if this chi-squared divergence remains bounded as n goes to infinity, then you're not going to be able to distinguish between, there's no sort of high probability distinguisher. On On the other hand, if the chi-squared divergence blows up, if it's little omega of 1, if it's tending to infinity, that means it's kind of inconclusive. We don't know either way whether you can distinguish. Okay, in this chi-squared oh, is that a question? Oh, no. Okay. The chi-squared divergence also has kind of a computational analog based on low degree polynomials. So, this is the chi-squared divergence is used to answer the statistical question. Is it possible to tell these apart? But what if we want to know, is it easy to tell them apart with a fast algorithm? Well, a lot of these same things have a close analogy here, but we're going to kind of restrict our attention to what's called low degree tests. So instead of using any function to tell these two apart, we're only going to use these kind of low degree statistics. And to explain what that means, here's an example. The triangle count in the graph is a degree 3 polynomial in the input variables. So here the input variables would just be like yij is a 0 or 1 that tells you whether the edge is present, whether the edge ij is present or not. So if I want to count the triangles in the graph, I have to sort of sum over all possible triangle locations of the product of these 3 indicators. Right, so that's one example of a test you can sort of encode using a low degree polynomial, but low degree polynomials can do all kinds of other things too. You can count larger subgraphs. It turns out you can also kind of implement some spectral kinds of arguments. You can essentially do power iteration on your matrix, and so on. So we tend to think that low degree tests are a powerful class of algorithms that potentially capture, all the fast algorithms that we know, if we're being a bit ambitious about it. And so there's kind of a low degree chi-squared divergence where basically you do all the same stuff, but there's something called the low degree likelihood ratio where you've kind of projected everything onto the subspace of low degree polynomial functions. And so, all the same stuff holds, but you think of this as sort of a computationally bounded version of the previous argument. Okay, and we tend to think of D as being something like log n or like slightly bigger than log n. Because the heuristic we like to use is that if logarithmic degree polynomials fail to solve a testing problem, then we call this hard. The reason being that a lot of powerful algorithms, or a lot of our best known algorithms, turn out to be captured by logarithmic degree polynomials. And that's kind of because when you do power iteration, you need like a logarithmic number of iterations to estimate the leading eigenvalue effectively. And so, yeah, the low degree heuristic would basically say that, if this low degree chi-squared is bounded, then the problem is sort of, quote, low degree hard, which means we, suspect that it may be kind of computationally hard to tell these two things apart. And, formally what it means to be low degree hard is basically that it implies that these kinds of low degree tests are not going to be useful, right? You're not going to be able to distinguish the two using triangle counts or other cycle counts or other kinds of low degree statistics. And again, if this thing is blowing up, if this goes to infinity, you don't technically know anything, right? It's kind of inconclusive about whether it's hard or not. But, in some but not all cases, this is actually a useful proof device in the sense that this thing is actually bounded in the hard regime, and this lets us, prove low degree hardness. For these cases where it blows up, sometimes you can do some like conditional argument where you condition on some high probability event to sort of fix it, but I won't get into that so much. Yeah.
Just, I'm not sure I get the middle equality where you go from P to Q when you restrict it.
Oh yeah, good. Is this one here okay? You're asking about this one. Why is this one true? Yeah, good. You're right. This turns out to be true, but I think it takes a little bit of a proof to do this. trying to think if I can recover this. Immediately, like it kind of has to do with the fact that yeah, I'm not sure I can recreate the proof of that on the fly, actually. But it has something to do with the fact that like the low degree likelihood ratio is, is a low degree polynomial. So it's like, oh, what do I mean actually? I guess when you take, yeah, okay, good. If we started here and you want to go here, you throw in a factor of L. So now we have low degree L times regular L, or think of that as the inner product between the low degree L and the regular L. The L has a low degree part and a high degree part, but those two are kind of orthogonal to each other. And so when you take the inner product, the low degree with the high degree gives 0. Yeah, good. Thanks. Okay. That's the proof of that part. Yeah, thanks. Other questions? So, all right, so if we start with this kind of statistical object, the chi-squared divergence, there's two different ways you can sort of truncate this to make kind of a computationally bounded analog. One way we've seen already, that's the low degree way, where you kind of think about likelihood ratios, but your space of function is restricted to these low degree tests. But I want to now introduce a second one, which is restricting things to low overlap. And that's what we are calling annealed Franz-Parisi potential due to some, kind of heuristic connections to some physics ideas, which I'll try to explain in a second. But what we're doing here is, restricting to low overlaps, as it says, right? So we take the chi-squared divergence, but we only consider the contribution from UV pairs that are that have sort of a small inner product. So this is sort of means like the typical UV pairs, right? If I draw U, just a random vector from whatever prior, draw V, another random vector, then in the typical case, you kind of expect these to have small overlap. Whereas maybe in some rare case, if you get lucky, they would be very close, they're the same. And so the second thing kind of means restrict to the contribution from the typical case. And the point here is going to be that, provably under whatever assumptions, we're able to basically prove that these two different types of truncations are the same, or are, the same up to lower order terms. Meaning that this very kind of algebraic perspective here of thinking about low degree functions is kind of the same as this much more like geometric perspective where we're more thinking about, I don't know, the landscape of the solution space or something. And I want to like kind of vaguely try to convince you that this looks, has some relation to these kinds of free energy diagrams that you might have seen if you're familiar with, AMP or these types of things. So if you ever worked with AMP, maybe you've seen a picture like this, where on the x-axis, we're plotting some kind of overlap between the true, between these two replicas. And maybe think of one of them as representing like the true planted signal, and the other one is representing like the algorithm's potential possible solution. And so as this thing increases, on the y-axis, we're plotting some kind of free energy. Right, a free energy meaning, which roughly means something like, how likely, right, I guess it's sort of the contributions to the free energy from the pairs that have a particular overlap. And so, we tend to think of an algorithm like AMP is kind of starting at 0 overlap, and it's kind of like a ball rolling down the hill. So in this case, it would be easy because the ball can kind of roll here, whereas in this case, you have kind of this free energy barrier. You're kind of stuck at the origin, right? Yeah, is this maybe something that's familiar? And so, okay, how does this sort of connect to this? You know, the connection is not like a totally strong one, but the function you should think about is like this last part, right? Just this, you know, contribution to the annealed free energy from things of a specific overlap, or sorry, this whole part really, you know, so this, or really maybe rather, sorry, the entire thing, I guess, because also we want to, you know, sum over all the things. So this function here, you can kind of think of that as being the one we're plotting, you know, as a function of delta. You know, maybe I should really put an equal sign here for the delta if to plot the function, right? I want to plot the contributions from some exact overlap for the thing. Okay, but what this is saying is kind of like taking the area under the curve between 0 and delta. By the way, I haven't told you what delta is yet, but think of delta as being maybe some kind of typical overlap you would get if you drew the u and v at random. Okay, so this thing is taking some kind of area under the curve, whereas the more traditional AMP picture would be like looking at whether this thing sort of tends upwards versus tends downwards. But in many cases, those two kind of coincide because we imagine plotting this on some kind of exponential scale, where like if you tend upwards, it means your values are actually getting exponentially big. And so when you take the area under the curve, you'll get something big. If you tend downwards, your values are becoming exponentially small. So if you take the area under the curve, you'll get something bounded. And so that's, you know, sort of the rough connection between those two things. Okay, so the formal sort of theorem here is that those two ways of truncating are kind of equivalent under various assumptions and for various types of models. And where we kind of think of this d, so the degree of polynomials here is some kind of proxy for runtime. So higher degree kind of captures more and more powerful algorithms. And sort of similarly here for the delta, as you take delta larger, this is sort of capturing more and more powerful algorithms as well. And here's sort of the way that these two should be connected. So you can kind of think of this as saying that, like, if I were just picking UV pairs at random, if I just sample a UV pair, sample another UV pair, and keep trying to do this until I get overlap delta, how long would that take? Right, or in other words, you know, the probability of happening once is something like this. So this is kind of saying that, like, you know, so degree D polynomials are roughly a proxy for algorithms of time, runtime, like e to the d. And then the corresponding delta is roughly the one where it would take you e to the d time to sort of see that overlap if you were just sampling stuff at random. Okay, and so the interpretation for this value is the same as for chi-squared divergence and everything, right? If this thing is bounded, if it's order 1, then we sort of will call this Franz-Parisi hard, which, you know, in some cases provably implies that it's also low degree hard. And then again, if this blows up, it's sort of inconclusive. We don't know. Okay. So, you know, to summarize this first part of the talk, so what was the point here? You one point or one message was that we, in some sense, connected algebraic hardness with some kind of landscape hardness. Of course, there are also some caveats that this new thing that we called the Franz-Parisi and annealed Franz-Parisi potential is not directly, it's not literally the same curve that you would use to analyze AMP and so on. So it's related in sort of a intuitive way, but not in a precise mathematical way, and kind of for a good reason, because the curves associated with the AMP are really about the recovery problem, whereas this Franz-Parisi does not necessarily say something about recovery area or mean squared error, because remember, the Franz-Parisi is really more tied to the detection problem. It's tied to the chi-squared and the distinguishing, which really is a different question from recovery. So for that reason, you maybe should not even expect the two to be related. But one thing that this FP does have going in its favor is that if you do this prediction, looking at the area under the curve, this really will make the right predictions for tensor PCA, matching low degree polynomials and so on, whereas the usual AMP machinery will not. And another sort of useful thing about this is that Franz-Parisi can be a useful tool for proving the low degree lower bounds, that instead of doing these kind of very algebraic computations, you turn it into a more geometric question, which is sometimes easier. And then very recently, there's actually been a new paper that kind of generalizes a lot of this stuff. They define some kind of more general version of this Franz-Parisi. They expanded the class of problems where these kinds of equivalence is known, and they also kind of connect it more directly to statistical query lower bound as well. Okay. Good. So yeah, questions about this first part of the talk. So now I want to move on to talking about AMP versus low degree estimation. So we're going to kind of step back and take a different approach. Like, I think, after doing this first thing with the Franz-Parisi, I think we can agree that it's not really quite a connection to AMP, right? Only in some sort of high level. So if we really want to try to connect low degree polynomials with AMP, we need to be answering the same question in both cases. So here we're going to really try to meet AMP on its home turf, which is the estimation question. And let's also just focus on one specific problem where we expect AMP to be optimal, and that will be the spiked Wigner problem, this kind of rank 1 matrix plus noise that I defined earlier on. And we know that the AMP machinery can make these very precise predictions about, exactly what is the mean squared error that you should get for a given value of the signal to noise ratio, right? In some kind of regime where that mean squared error is converging to like a non-trivial constant. I suppose I'm kind of like assuming maybe that you have some familiarity with AMP and stuff. I hope that's sort of okay, but yeah, ask questions if you have them. And so I think now, coming from the low degree polynomial perspective, I think for a start, the first thing we'd like to do is to just see, can we actually recover those same predictions using low degree polynomials? So here's just the spiked Wigner model. Again, we're going to take this model, and let's try to define what would it mean for a low degree polynomial to solve this, to really solve the estimation question. And so we're going to think about a multivariate polynomial that takes in the matrix Y, it outputs a number, and that number is supposed to be like an estimator for this U1. So let's just try to estimate the first coordinate of the signal vector. Because once we can estimate the first coordinate, then by symmetry, we can just as easily estimate the second, or third coordinate. So it's sort of sufficient to think about this one. And so we're going to measure our success with mean squared error. We're going to say, among all degree D polynomials, take the best one and measure, what mean squared error do you get for estimating the U1. Okay, so this is sort of like a definition of a success for low degree polynomials that sort of aligns well with what with the task that AMP would be trying to do. So this is really for, recovery now rather than detection. Okay, and so, what does AMP actually do for the spiked Wigton model, or what does it achieve? So the setting I'm going to think about is where the signal vector U is going to be drawn from some prior, where each coordinate is drawn IID as some distribution pi. And I'll assume that the distribution of each entry is not zero. It's sort of biased, let's say it's positive. For example, this is to avoid some kinds of technical issues, like maybe you've seen that if you have a mean zero prior, then AMP needs some kind of a warm start to get off the ground. You need to maybe do like a spectral initialization or run it for a logarithmic number of iterations or something. And so this setting kind of avoids that problem. So here AMP will be able to succeed in a constant number of iterations. And by AMP, I'm going to mean like the Bayes optimal AMP, the one that has those, the internal functions that it's applying. These denoisers are chosen in sort of the Bayes optimal way, like some kind of conditional expectation. And we'll run this for t iterations for a constant t. And I'm going to be interested in what happens in this double limit where first n, the problem size goes to infinity, and then the number of iterations goes to infinity. So think of this as being like we run the AMP for a large constant number of iterations. And when you do this, here's the picture of what kind of estimation accuracy you get as the SNR, lambda increases. This is like the picture for one specific choice of the prior pi that's like supported on 3 different points. Not so important what it is. But what's going on here? So the blue curve is the Bayes optimal mean squared error, or maybe this is more like 1 minus mean squared error. So higher is better here. So blue is Bayes optimal, whereas the black is AMP. But the blue curve is like hidden behind the black curve in these 2 regions. So AMP, when you're either here or here, we know that AMP is just information theoretically the best possible thing you can do. There's kind of nothing more to say. But in the middle, we have this gap, right? So if you're kind of in between these 2 phase transitions, the AMP error is not so good, whereas the optimal Bayesian error is a lot better. And so the question we're sort of asking here is, can you do better than AMP, right? We know that if you have a slow algorithm, if you do a brute force search, you can do better. But can a fast algorithm do any better than this precise black curve here? And so the kind of conjecture that I think has been around for some time now is that we kind of think AMP should be the best possible mean squared error among all polynomial time algorithms. What we actually prove is that AMP has the best possible mean squared error among all constant degree polynomials. So if you take any constant degree polynomial, you're not going to be able to get any better than this exact, curve right here. But the constant degree is sort of a limitation of the proof techniques. So really, I believe that AMP should be the best even among much higher degree polynomials, even when you go to degree almost n. And then once you get to degree n, then polynomials start to be able to capture like brute force search, and you should sort of jump up to here all of a sudden. But that's, this is what I believe should be true, but that part's not proven yet. But okay, why is this true? Why do AMP and low degree polynomials give exactly that same mean squared error curve, right? There must be kind of a good reason for this. And in a nutshell, the reason is basically because AMP is equivalent to some subspace of polynomials that we call tree-structured polynomials. So this is maybe a picture to illustrate the difference between, what's a tree-structured polynomial and what's not. So remember, these are polynomials that take in a matrix Y as input. So these would be some examples of the types of monomials that might appear. And for each monomial, you can sort of make an associated graph. Vertex 1 is special because we're trying to estimate vertex 1. So you kind of think of these graphs as being rooted at vertex 1. And so, if I see Y sub 1, 3, I connect edge, connect the vertices 1 and 3 and so on. And so tree structured means monomials whose graph is, doesn't have cycles, whereas non-tree would be anything else, right? So if it has a cycle or a double edge or something. And then tree-structured polynomial means like any linear combination of tree-shaped monomials. Is that okay? And what turns out to kind of be true is that, within the space of all polynomials, tree polynomials are kind of equivalent to AMP. So in one direction, if you take the AMP algorithm and sort of approximate it by a polynomial, you effectively get a tree polynomial plus some lower order terms. And sort of on the converse too, if you have any tree polynomial, you can sort of construct an AMP scheme that computes it. So those two things are kind of tied together. And then furthermore, in the spiked Wigner model, we're able to show that tree polynomials are all you need. That the mean squared error you get from the best tree polynomial is the same asymptotically as the best you get from any polynomial of that same degree. Okay, and that part's very specific to the spiked Wigner model, and much of the core of the proof is there, but in the interest of time, I don't think I can say much more about that. So I guess, looking forward, first of all, yeah, questions about any of this? So this, kind of explains why we were able to, show this kind of equivalence between AMP versus low degree polynomials. But it wasn't totally satisfying because we only said that constant degree polynomials can't beat AMP. We'd really like to say that much higher degree polynomials can't beat AMP. Maybe n to the power of some fixed positive constant, for example, would be a good start. And we do have some progress at higher degree, which I'll kind of give you an overview of some of the results we have. So we are able to show that low degree polynomials match some of the sharp phase transitions that were first predicted in statistical physics. But here we're not going to match the exact mean squared error, right? So this is more about predicting what's the value for lambda, where suddenly you start to get non-trivial recovery. Right? So in the spiked Wigner model, okay, now going back to the situation where the prior is mean 0, so that you have kind of this BBP transition, like at lambda equals 1, you go from, being able to do no recovery at all to suddenly you can do some non-trivial recovery. And that's all, this BBP transition, is what, AMP would predict is the threshold, computational threshold. And indeed, we can now show that low degree polynomials also start to achieve non-trivial estimation at that same point, even for this kind of higher degree. And this also extends to like a more general class of Wigner models than the physics methods have kind of analyzed. So you can even take like spiked Wigner with a growing rank, as long as the rank is sort of smaller than n. BBP turns out to still be the right threshold. And then another similar result for a stochastic block model. So this is like community detection in graphs. Okay, I haven't defined the model formally, but maybe some of you have heard about it, right? This is some random graph with like densely connected clusters. And there's this famous Kesten-Stigum threshold, predicted first by Florent and others, where the fast algorithms start to work. And indeed, we can show that low-degree polynomials also start to work at that same spot, even for like a growing number of communities. So as long as the number of communities grows smaller than the square root of n, the KS threshold still remains the low-degree threshold. Okay, and why square root of n? Well, actually, once you get to more than square root of n communities, it turns out you can actually start to beat the KS threshold. So something really changes at that point, and there's actually a better algorithm that goes below this. So I think one thing that's kind of exciting about this is that we're able to make these predictions. We confirm the physics predictions, but we also kind of go beyond them into these other kinds of scaling regimes where it's not so clear that the physics predictions actually work. But using the low-degree polynomials, we're able to sort of figure out what's going on there. Yeah.
Just here, is it for detection or recovery or both?
This is all about recovery. Yeah, for this growing number of communities, the recovery and detection thresholds are not the same. So when you have a lot of communities, it becomes very easy to do detection just by like counting triangles and stuff. So yeah, everything here is really about estimation, like using the low degree mean squared error as defined like a few slides ago. Thanks. Yeah, good. Other questions? Okay, so I think I'm about out of time, but just to wrap up here, we know AMP makes these really great predictions that are very sharp and tell you exact mean squared error and stuff. But they're also not applicable to all settings like tensor BCA and certain scaling regimes like growing rank and so on. Low degree polynomials give in some sense a stronger form of hardness. You can think of that as ruling out all polynomials rather than the restricted tree polynomials. But the current results we have are less sharp than an AMP, and it's been somewhat difficult to try to prove these really sharp results in the low degree framework. And so that's sort of an ongoing challenge, is to sharpen the low degree results to presumably match AMP, and in the process we can kind of start to understand when AMP is the optimal algorithm and in which cases is it not. Yeah, thanks a lot for your attention.